Mathematical equations or models that are derived from the principles of science and engineering need to be solved in order to determine values of parameters necessary in certain applications. If we have a certain equation wherein a function of x is equal to 0, the values of x that satisfy this equation are the solution to this equation. Normally, we call these values of x as the roots of the equation. If we have this graph, to visualize where the roots are located, the roots of the equation are the points in which the graph touches the x-axis. This graph here is a second degree polynomial in x, or a quadratic equation. So years ago, you know that the roots of this polynomial function or polynomial equation can be solved using the quadratic formula. So the visual representation of the roots are this. We have two roots of this polynomial function or polynomial equation. We have x sub 1 and x sub 2. So the roots of this equation is, or the solution of this equation is a piece of cake, because we know that a quadratic formula is already derived. How about if we are given with a much more difficult function or higher degree polynomial? The roots of these equations would be very difficult to determine. So here comes numerical solution to help us find the roots. An equation can have no solution, one solution, or many solutions. Generally, the methods used in solving equations numerically can be divided into two groups: the bracketing methods and the open methods. In this video, we will explain the bisection method, which is a type of a bracketing method. If we plot f of x versus x, we know that the true solution is located here. In bracketing methods, the idea is to guess two initial values of the solution. That is, having an upper bound value of x and a lower bound value of x, which we will denote as a and b. This interval AB should include the true solution of the equation. And in bracketing methods, certain procedures are employed in order to get nearer and nearer to the true solution. These bracketing methods make use of the fact that near the vicinity of the true solution, the value of the function changes in sign. First case of this idea is that, for example, in this case, the value of the function here is positive and the value of the function at b is negative. In second case, in the interval AB, the value of the function at A is negative and the value of the function at B is positive. One of the bracketing methods is the bisection method. We will show how the bisection method is employed in order to locate or to find the root of an equation. So if we have a plot of the function, certainly the root is located here. So we will initialize two guesses that bracket this true solution, since that is the idea of bracketing methods. So we initialize two guesses A and B. So that is our first interval. The idea of bisection method is that we will get the midpoint of the interval AB. So the midpoint of that interval is here. And then we will project that midpoint is the first estimate of the solution. So this is our first estimate of the solution. Now notice that the value of our function at the first approximate solution here, the value of the function is positive. So what interval are we going to use next? Is it this interval here or the other side of the half of the interval of the first interval? Since the value of the function here is positive and the value of the function here is also positive, the root is not located here. The true solution or the true root is located here. Therefore, we will again bracket that true solution, and our next interval will be this portion here. And again, following the same procedure, the midpoint of that interval will be the second estimate of our solution. Now take note again that the value of the function here is positive. And the solution or the true solution is here. Therefore, our next interval will be located here. Following the same procedure again, the midpoint of that interval and locating its midpoint, that will be the third estimate of our root. So notice that the value of the function at the third estimate of the root is negative. The true solution is located at this interval. Therefore, our fourth interval will be located in this portion. And notice that the midpoint of that interval is approximately or maybe equal to the true solution. This is the idea of bisection method, wherein the first initial guesses AB will be the upper bound and the lower bound of the interval, and then getting its midpoint, or we are bisecting this interval here. The interval is being bisected, and that bisection will be the first approximate of the root, and again bisecting the second interval, that will be the second approximation of the root, getting the third interval and getting its midpoint again, or bisecting that interval again, will be the third approximate of the root. And lastly, at the fourth interval, the bisection of that fourth interval is now getting closer or maybe really equal to the true solution of this equation. The algorithm of this bisection method will be this, the example of the algorithm of the bisection method is shown here. So first, you choose a first interval such that a solution exists between them. So mathematically, in order for that interval AB to be bracketing the true solution, f of a, or the function at the value of the function at a and the value of the function at b, should have different signs. This is illustrated in our illustration here in the bisection method, that the values of the function at a and b, notice that the value of the function at a is positive and the values of the function at b is negative. Therefore, the product is negative. The next interval, at the interval 2, the value of our lower bound the value of the function at the lower bound value of x is positive, and again, use the same value of b in the first interval. So that is the idea, or that is the checking, so that the solution should be bracketed by your interval AB. Now, after having that checking, calculate the first estimate of the root. We will denote x sub r as the midpoint of the interval, which is a plus b over 2. Now, for the next step, determine which subinterval the true root lies by making the following evaluations. So first, if f of a times f of xr is less than 0, that means negative, the true root lies between a and xr. Therefore, set b equals xr. Okay, for our first interval, the midpoint is here. For the first interval, the midpoint is here. So this is our xr. We will denote this at xr1. Okay, so at xr1, the value of f of a is positive, and the value of the value of f of xr is also positive. So note that the idea here is, if f of a times f of xr is less than 0, the true root lies between a and xr. That is not the case here, because the value of the f of xr times the value of f of a here is greater than 0. Therefore, this is not the case here. We will read sub-step B. If f of a times f of xr is greater than 0, the true root lies between b and xr. Now, that is the case of our illustration here. The value of f of xr multiplied to our f of a is positive or greater than 0. Therefore, this is correct. The true root lies between b and xr. So b and xr, the first estimate of the root, the true root lies here. Therefore, the checking should be that that the value of the function multiplied at the lower bound and at the upper bound should be negative. This is the checking. So therefore, set a is equal to xr. So in our illustration, we set xr1 to the value of a. So notice that our second interval here now is here in this portion, because we set a here and retain b. Okay, and third substep is that if the product of f of a and f of x are equal 0, actually that should be that should just be an approximation, or which is approximately equal to 0. So we change it as approximately equal to 0, or a specified criterion is attained, terminate the computation. So how about its termination criteria? If, for example, we know the true solution of the equation, you can get its true error, true percent error. But generally, why do we have to use numerical solution if we know the true solution? Right? So this is not always the case. You cannot always find, or you cannot always determine the true percent error of the equation. So what's another alternative? It's by using the approximate relative error. This approximate relative error is determined using the values of the calculated approximate solution, which is the new approximate solution minus the old approximate solution. Then you will get the approximate relative error. That is why it is called relative. It relates the value of your current approximated solution to the past approximate solution. So as an example, which is given in your modules, determine the solution of the equation 8 minus 4.5 multiplied to quantity x minus sine x by using bisection method. So again, we will use a stopping criteria since we cannot really, if we really want to um, get a more and more accurate solution, you can solve forever. But that is not the case because you will be computing forever. So we will use a certain stopping criteria. So use this stopping criteria should be, or this epsilon sub s equals 0.5% is defined as the stopping criteria wherein your approximate percent relative error should be less than or equal to this stopping criterion here. So create a table that displays the values of a, b, xr, of f of xr, and the approximate error for each iteration of the bisection process. So since we are using numerical solution, we will plot the equation for us to determine, or we will have an approximate location of the solution. Here we use the available graphing calculator from the internet, which is Dismos, a graphing calculator by Dismos, which is plotted here. So from the plot of the plot of the equation, we know that the solution is here, somewhat in between. The initial interval is chosen as a equals 2 and b equals 3. Thus, because it brackets the true solution, which is somewhere here. So in iteration 1, since the initial guesses are 2 and 3, so our first approximate solution, or xr1, is a plus b over 2, that is 2.5. So the value of the function at xr is this one, and the value of the function at a is here. So that is negative and positive. Therefore, the product of the function at a and xr is less than 0. So what are we going to do? Since that is negative, set b equals xr and retain the value of a. Now we will proceed at the second iteration. So at iteration number 2, the new values of the new subinterval are, since we retain the value of a, which is equal to 2, and we set b equal to xr. Solving further, we get the second approximate of the solution, which is 2.25. Now, following the same procedure, we get the value of the product of the function at a and xr, which is greater than 0. So from the algorithm that we provided, we will set a is equal to xr and retain the value of b. Since we have two values of the approximate solution already, we can determine its approximate percent relative error, which is calculated using this formula. Using the new and old estimated root, we get that the percent relative error is at 11.11%. Solving further, at iteration number 3, so the process is continued until the value of the percent relative error is less than the specified termination criterion, or the stopping criterion, which is 0.5%. I will show you the table of values of this solution. So at iteration 1, we initialize two values, or two initial guesses, which are 2 and 3. Our first interval is 2 and 3. And at iteration 7, we get 2.49688. So the value of the approximate percent relative error is less than the specified stopping criterion. Therefore, take the estimated root at as 2.429688. This is because our approximate percent relative error here is now at 0.32%, and we specified that the process or the algorithm stops when the percent relative error is less than 0.5%. However, you can still continue your process if you want to, and you get more and more refined estimates of the root. That's it. That's the bisection method works in finding solution of an equation.